Hi, welcome to today's session on reinforcement learning. In previous talks, you have gone through familiar models of machine learning that involve supervised models like classification and regression models, or unsupervised models involving clustering and rule mining. Reinforcement learning is a slightly different paradigm, and it becomes clear when we try to apply it to a real-world learning task. Let's say if we look at how did we learn cycling, we didn't use either of the technique. We didn't have samples available to us. Uh, what we really did was to learn it through trial and error. So we learned how to balance on two wheels. And sometimes we had positive examples where we could do a very good balance. Or sometimes we fell down and we realized it really hurts. And from those mistakes, we figured out, how one could cycle very well. Uh, the same can be applied when you try to learn a new game. You might know the moves or the rules of the game, but in order to win against an opponent, you have to play the game many, many times. And from your experience, you will learn how to, make uh, how to take decisions so that you can win. Now, this is the outline of the talk. We'll give you an introduction to reinforcement learning. We'll start with multi-arm bandits, which are a necessary or stepping stone in order to realize the potential of reinforcement learning. Contextual bandits, it's a little more sophistication on top of multi-arm bandits. And these algorithms are quite popular in e-commerce or web domain. Finally, we'll come to RL and introduce a couple of popular algorithms there. We're also introduced to deep RL, where we combine the representational power of deep neural networks with the decision-making ability of reinforcement learning. So a reinforcement learning can be thought of an interaction between an agent and an environment. The agent is placed in an environment, and in most common cases, it doesn't have a perfect knowledge of the environment. The agent can take certain actions which will have an impact on the environment, and depending on how the action is, how good the action is, it will be awarded a reward. Now, to make a more concrete example, let's look at a self-driving car where the agent is the software or the decision-making system which is embedded in the car, and the car can, by virtue of some sensors that are mounted on the car, it can take a picture of the environment, for example, and it might know whether it is placed in a crowded street or an empty street or at an intersection. And it can take certain decisions like whether to turn left or accelerate or slow down. And finally, we have a reward structure defined on the car that if it is able to reach the destination without an incident, we give it a positive reward. In case of any other incident, we uh, offer a penalty. What makes RL different from, say, supervised learning is when we look at the definition. So supervised learning, we're given a training data set where we have inputs X and output Y. The output can be either binary or nominal or maybe a real target for regression. And the assumption is that data is IID, so it has been sampled independently from the same distribution. In case of reinforcement learning, we don't have often we don't have any training data to start with. The part of the learning is to do both, to collect data which will eventually prove useful for making good decisions. At the same time, not to make too many mistakes while we are collecting the data. And of course, it's a non-IID setup because the decision that we take now will have an impact in the future data points that we will collect. Levels are known in reinforcement learning, rewards are unknown. Sometimes they're stochastic because I might take the same action again, but because it was in a different state, I might get a different reward altogether. The goal for supervised learning is to maximize the number of correct predictions, and there's no concept of a look ahead for supervised learning. In reinforcement learning, the objective is often to collect the maximum rewards in the long run. So that involves some explore and exploit dilemma that we will look at later. Essentially, what it says that we cannot be very short-term focused or myopic because we need to collect good data, which will help us to make better decisions in the long run. What it also means that in the short term, we are willing to make some compromises, maybe make some mistakes, which we will be able to compensate for in the long run. Examples where supervised learning is more often used is, for example, STEM classification or object detection, whereas reinforcement learning or its variants are traditionally used in many ranking or recommendation problems. We'll look at an example of what could be a potential use case for reinforcement learning. Let's say we have an e-commerce site uh, and customers are coming on the site where we feature some deals. Um, and if the customer likes those deals, they click on it and they might explore and then eventually purchase the deal. If they don't like it, they will go and shop elsewhere. Right? Now, one thing we can do is if we are very much focused on short-term rewards, so we'll try to promote deals which are probably will give us higher revenue, right? Um, now, the customer might buy it once, but they may not buy for a long time in future. They may not even come back to the site. For example, if the product is not really of good quality, they may not come back to the site. So the other way, if you're really optimizing to for long term, what would have been is to recommend a really good product, something which may not give us an immediate value. For example, it can be a Kindle, which may not be as expensive as recommending a smartphone, but uh, customers will enjoy and they might shop for the device to buy, say, ebooks over time, right? So although we're making a not making a very big short-term reward, but it's something the customers will like, and they will be willing to, spend on this investment over a long period of time. So it will give us eventually long-term reward. Now, there are some achievements of reinforcement learning, and if you go through these examples, you'll see most of these are on game playing uh, environment because it's very easy to collect data and train an RL agent. Um, One thing to note here is in all these cases, the performance was better, than could have been obtained by any other method involving the supervised learning method. And in many cases, it was obtained without any human instruction. So what it means is, even from collecting the data, which are the raw sensory feeds, then converting that to an useful information that the agent will understand, and then making decision on top of that. This end-to-end training was done without any supervision in mind. So now again, we're looking at this familiar diagram where we have an agent and environment. Uh, Now we'll use some notations here. So at each time state, the agent observes a state st and it executes an action a suffix t, right? And uh, the environment will receive this action from the agent and it will decide what will be the reward that can be offered to the agent. So these rewards we're using R suffix t for denoting the reward. And this interaction sort of carries on over time. Depending on how good or bad the reward is, the agent gets a sense of what are the meaningful actions to take uh, for a given state. Okay. Now, Markov decision process or MDP is an abstraction for modeling the sequential decision-making behavior for an RL agent. And MDP is defined by five tuple, which we will go through uh, uh, at a time. Now, it has a set of states S, which captures the agent's knowledge of the environment. It has a set of actions that the agent can take, or it's a universe of actions the agent can take at a given state. Though it's possible that you can have some additional rules, that says, okay, on certain states the agent is not allowed to take some actions, right? Then you have a set of transition probabilities that says, okay, given the current state and the fact that the agent took um, an action A from this state, what is the probability that the system will end up into a state S prime, right? So if you look at this example, this MDP has unrolled into four different time steps. So the first state, the state is S0, and the agent has taken a decision A0, right? And depending on that, the the transition here is S1, which is actually a state uh, that the environment has reached a condition of its previous state and the action that the agent has taken. Similarly, on S1, the agent takes an action of E1, which moves the system to a state S2, and it continues. The set of rewards are offered, the set of rewards are the population of all possible rewards that can be offered to an agent. Uh, the reward depends on the current state and the action that the agent takes. And then finally, gamma is the discount factor. So it gives control to the modeling, to the modeler, how much importance one should assign to short-term versus long-term reward. For example, if your gamma is very small, very close to zero, then you are essentially, you know, kind of ignoring any long-term reward. You are very much focused on what is the reward you want to collect in short term. If your gamma, as your gamma increases, so your horizon that you are looking to collect the future rewards also increases. And that is made more precise when we look at the objective of the agent is to maximize this quantity. So this is a discounted cumulative expected gain, or the discount is achieved through the geometric series over gamma on future rewards. uh, and it's cumulative because we're looking across rewards collected over multiple time steps. And then we are also taking expectation because many of these quantities are stochastic in nature. Now, this discount factor is needed because we're uncertain about the future. We may not know what is the price of a stock after 2 years. Um, Sometimes uh, we might prefer to collect more rewards sooner than waiting forever. You you want to collect some rewards now. Uh, and it can be for mathematical convenience because uh, without sometimes, if there is no discount factor, this some uh, some of the expressions may not converge. So it's purely for mathematical convenience. We will need a discount factor. Now, exploration is as fundamental to any reinforcement learning problem, and this also introduces a dilemma. Uh, the decision-making system, it involves choice between uh, exploration, where we gather more information. We try out something new, and depending on whether it was a good or bad action, we collect a reward. But it also tells us what is a good or bad action as well. Exploitation is when we just make use of a knowledge that is collected from previous steps, and like you take the best decision given the correct information, right? So we can, for example, recommend the item which is most profitable. Now, often it happens that in order to collect uh, or win over a long-term um, strategy, it might require some short-term sacrifices. So we might be willing to, not collect enough rewards in the short term. Uh, but this will be compensated when we, take the decision many times over a long period of time. Um, and the goal here is to gather enough information in the first few iterations or in the short term to make overall best decisions. Okay, and this is not very specific for reinforcement learning. In our day-to-day decision making, we often exhibit this behavior. Like if we want to go to a restaurant, once in a while, we may want to try a new restaurant, right? Which corresponds to exploration. If a new restaurant has opened up recently and we're not sure about it, we may want to try it out. And if we like it, it might become my favorite restaurant, right? Or if you're very unsure, like if you're taking your guest, you might want to go to a restaurant where you're more confident. So take them to your favorite restaurant, right? Similarly, for other scenarios like listening to music or when we are deciding what ads to show, again, explore and exploit will prove extremely useful there. Now we'll move into multi-arm bandits. So these are very much of a simplification for the MDP that we saw in reinforcement learning. So a multi-arm bandit is a tuple which has action and reward pairs, where action is a known and finite set of actions. Like if you imagine there is a casino and there are different arms that you can pull or levers you can pull. So all those levers become your actions. And then depending on the way the casino is uh, wired, you might get a reward by pulling a lever, right? So that reward, the set of all possible reward, is determined by capital R. So A is a known set or a known and finite set of actions, and R is an unknown probability distribution over rewards, which is conditioned on the action taken, right? So the way the interaction happens, for every time state, we will, uh, the agent will select an action from the set of possible actions, um, which is A suffix T. And depending on the action that we have selected, the environment will determine a reward, right? So here the reward depends on the action on. And the goal is to maximize the expected cumulative reward, that is sum of rewards that is collected over a time horizon. Now, the difference between multi-armed bandits and RL can be realized when I look at their MDPs. So in RL, we have states. The reward depends on both the state and the action. And of course, there are transitions between states depending on the actions we have taken. Now, the biggest difference in multi-armed bandits is there are no states here. So we are at any point of time, we uh, take an action and observe a reward, which depends only on that action. Okay? So this is the assumption in the modeling. Now, as there are no states in a multi-arm bandit setup, so the actions that we have taken in the current state, it does not, directly influence our rewards or long-term rewards. which is why it's a common practice not to involve in a discount factor here in the objective of multi-arm bandit. Now, while we have looked at multi-arm bandit from the point of view of reward collection, but if you explore the literature, you will encounter uh, uh, it is uh, it is the objective there is to what is known as minimizing regret. Now, why is regret or this new definition is required is because sometimes the sum of rewards is not very informative because it doesn't tell us how far we are from the optimum reward. Now, what it means by optimum here is if we knew which arm was the best arm, right, we could be pulling that arm all the time, right? And that would be my optimum strategy. So just knowing the total rewards that we are collecting doesn't really tell us how good, how close, or how far we are from the optimum reward we could have collected, right? So if we look at the uh, mean reward for an action A, which we'll also call as a value of the action A, can be written as this expectation. And then the optimal arm would be the arm that gives us the maximum value, right? Of course, this assumes that we know the distributions, reward distributions, which helps us to calculate the value of an arm and hence the optimal arm. But in real life, we wouldn't know that, right? But I can still write the total regret as the difference of two quantities. The first expression is the, the maximal reward that I could collect. So it's basically saying that we would pull the optimal arm for all the t time steps. And the right side is the reward that is collected by the agent, right? So the difference is the total regret. Now, it can be shown that minimizing the total regret is equivalent to maximizing cumulative reward. So it's just a notation, and I'd say regret is more informative because it also gives us a sense of how close to the optimum we are. Okay. So there are plenty of application for multi-arm bandit, uh, like in recommendation, where each item that we want to recommend becomes an arm, and whether customers are clicking or purchasing that product could be the reward. Similarly, for advertising, here, at the top of the search result, there could be an ad shown. And again, these ads could be, you know, each ad becomes an arm. And again, click on the ads will be the reward. I will look at some popular algorithms for multi-arm bandits. The simplest one is called Epsilon Greedy, and what it does is at at every time step, it makes one of these two decisions. It can select one of the arms randomly, right, with the probability epsilon, and hence the name Epsilon Greedy, or it can pick an arm that it so far knows to be the optimal one, right? So which is what we call this best arm, which is pulled with a probability of 1 minus epsilon. So if you look at it, it sort of unrolls in this flavor. You start, and then with probability epsilon, you pick a random arm, and again, you can pick one of these arms randomly, or depending on what you already know, you pick the best arm, right? Now, it is simple because it's sort of very friendly to productionize such an algorithm because you might already have some rules, or even a model we'll see later. And you can instantly convert that into a bandit algorithm, right? Just allow this exploration or data collection through this branch. Right? Now, how do you set the value of epsilon? So that's more of an art. So you can start with the common practices. You start with some value and then reduce it over time. Now, whether you reduce or not, that depends on how stationary the environment is. So in a sense, if you're if the environment is not dynamic, right, it is stationary, your reward distributions are not changing over time, then it makes sense to reduce exploration over time, because as you iterate or interact more and more with the system, you will be collecting knowledge which will prove useful for decision-making purpose. But if a system is also evolving, or it's non-stationary, then you might have to do an exploration continuously over time. So there are various strategies, like you can have a pure exploration where you just explore maybe the first n number of steps, and then after that you stop exploration and take the optimal decision based on what data you have collected. Or you could reduce epsilon that we saw in the previous slide uh, in a certain way, which will which will sort of minimize the unnecessary, because there is also a cost for exploration. If you explore too much, more than what is absolutely necessary, then obviously you are making a short-term losses. But at the same time, you're also limiting your opportunity to make any long-term gain. Then there are also adaptive strategies where, depending on how the system is evolving, you may lower or increase exploration percentage. Now, upper confidence bound is uh, a more principled approach to multi-arm bandit problems. So here, the assumption is that the reward distribution is generally unknown, and to know the or to estimate the reward distribution, we have to draw samples from it. So let's say we look at a particular arm, a suffix k, which is pulled. We have drawn that arms in suffix k number of times, and we have observed a sequence of rewards. Those rewards are basically sampled from the corresponding reward distribution, so they may not be same value. Depending on how what is the variance of the distribution, these rewards can be quite different. Now, we can estimate the mean reward of that arm by a sample average. The question is, how good is this sample or estimated mean reward is to the true reward? So we can look at some simulation where the reward distribution is a normal distribution with mean of 10 and variance of 100, which if you look at the PDF, it would have this kind of bell shape. And we can also look at the distribution. So if you see here, this blue one is the distribution of rewards, and the red one is the distribution of the mean reward that we have estimated after drawing 10 samples from this blue distribution, right? Now you may ask why this mean reward is um, how does it give a distribution? Because here it's just, so what we'll see is how this distribution changes when we allow drawing more and more samples. So if we go from 10 to 100 samples and then 1,000 samples, what basically changes here, this distribution in rate or sample distribution gets narrower and narrower as we become more and more confident about the estimate, right? So the upper confidence bound algorithm is based on our estimate of sample rewards. So let's say each arm is pulled n number of times to observe some rewards. And based on that, we will estimate a sample reward. through simple averaging. Now, this leads us to a construct called confidence interval. A confidence interval will have these two limits, low and high, and then at the center, we have our estimate. Okay, and this interval is constructed in a particular way uh, so that this property kind of holds. Okay, and this one, the upper end of the interval, is called upper confidence bound or an arm, or in short, UCB. So this is how the algorithm process. For each arm, we need to pull it at least once and observe the reward. And we maintain a few counters. There are two sets of counters, one for the number of times we draw an arm, and the second counter is to that stores the mean reward we have observed till this point for each arm. Now, for every iteration, we calculate what is the UCB of an arm, which is essentially what goes under this argmax here. And the arm which has the highest UCB is selected as the candidate. And this arm is pulled and we observe the reward. And depending on the reward, we update these counters. Okay. Now, if we look at this expression for UCB, so there's something interesting here. The UCB will be high when the first term is high, which means the arm gives a high reward, or its estimated reward is high. It can also be high. The UCB can also be, pulled higher if by virtue of the second expression. And the second expression, especially if you look at the denominator, if an arm has not been pulled for enough number of times, then this will dominate. The second term will dominate. And this is how, intuitively, the algorithm achieves a balance between exploration and exploitation. So the first term here is exploitation. This is based on what our experience tells us, based on the rewards that we have seen in the past. The second part in the expression is based on exploration. So we are favoring arms which are not drawn sufficient number of times, okay? Because their in value is quite small. So here's an example of upper confidence bound, the algorithm in progress. Let's say we have three arms, A1, A2, A3, and this is how the distribution of sample reward looks like. So if you look at in terms of the mean reward, A3 is the highest, but when we factor in the UCB, it's the arm A1, the one in blue, has the highest UCB. So as per the UCB algorithm, we will uh, pull the arm A1 and observe its reward. Now, what it turns out in this particular simulation is that this arm, after pulling this arm, we observe a very little reward, uh, which sort of shifts the distribution a bit. Now, if you try to make out a difference between the figures at the top and the bottom, the the blue one, the arm A1, not only the distribution has shifted towards the left, but its variance has also reduced quite a bit. Okay, so now in terms of mean as well as in terms of UCB, it is clearly inferior to the arms A2 and A3. So next time we are going to decide the arm which has the highest UCB, we'd probably be pulling the arm A2. Okay. Now we'll come to Thompson sampling. Uh, um, so before we get to the motivation of Thompson sampling, let's look at an example. We have two arms which has been pulled exactly the same number of times, and we have the sample rewards estimated for them. Now, the key question is, are we confident about ARM A2, or should we continue to pull A1? Now, without any additional information, it might be hard for us to make a decision here. So what we do is to assume some form of prior distribution on min rewards. So what it means is, um, if we look at the um, reward distribution across the arms, they follow this distribution. The reward is typically around 2 with some variance around it. And since this is pretty far from the mean, this gives us some sense that probably we should continue to pull A1, you know. So Thompson sampling is a Bayesian approach to multi-arm bandits. What it does is just like uh, unlike UCB, here we assume a parametric form of the rewards. We say that for the reward distribution for on A, it is controlled by a distribution with its own parameter. Now, this parameter is unknown. What we are also given is a distribution over this parameter, which we call a prior. Okay. Now, the key steps that is involved in Thompson sampling is to compute a posterior distribution of rewards, which is this, uh, which we'll arrive at by applying the Bayes theorem. We'll see that later. And then you use the posterior distribution to guide our explore-exploit scheme. Now we are making distributional assumptions both in the reward models as well as on the prior. And if those assumptions are correct, then this technique can give us improved performance. Okay. So the Thompson sampling algorithm processes this way, and if it sounds a little abstract at this point, we'll look at an example just right after. What we do is we apply Bayes theorem to invert the probability. So now we have a probability over the parameter, and with what we use to draw samples from this posterior and use that sample to compute the value of an arm. Okay. Now, whichever arm has the highest value, that arm is selected in that point of time. We'll look at an example with Thompson sampling in action. It's a classical problem of recommending product to customers, where each product, and okay, yeah, the goal is we want to recommend products so as to maximize the number of purchases. So here, each product is an arm. The rewards are binary. We have either purchase or no purchase. For binary rewards, we can model it as a Bernoulli distribution. So Bernoulli distribution, it has a parameter between 0 and 1. It specifies the mean reward. So you can think of it as like uh, we toss a coin with this parameter. If the coin turns up with head, we assume that the customer will purchase the product. Okay. Um, Now, for Bayesian analysis, we would need a prior distribution on this parameter. So what sort of prior distribution do we use here? So as it turns out, we would use a beta distribution as prior. Well, it has several which has this form, by the way. So it has a term theta and 1 minus theta with some hyperparameters, this alpha and beta. And depending on the values of alpha beta, you can have different shapes of the beta distribution. Okay. Now, why do we use a beta distribution? Yes, it turns out there are some advantage. First of all, we need to sample a probability from this distribution, which means the value should lie between 0 and 1. Had it been some other distribution, for example, most common, let's say a normal distribution, we cannot guarantee that the support will be between 0 and 1. So that's one reason. The other reason, as our analysis will show later, this is a conjugate prior for binomial distribution, which simplifies our analysis to a great extent. Now, what we're going to do is to Look at this posterior, which is proportional to the product of likelihood and prior albeit normalization term. Now we'll plug in the expression for likelihood and prior individually, and we'll see how our choice of prior is actually helping us to simplify this calculation. Okay. So before that, we'll use some notations. Let's say n suffix x and t, that represents the number of impressions of product x in the first t time steps. P suffix x and t, it represents the number of times the product has been purchased within the first t time steps. Okay. Uh, with these notations, you can write this likelihood term the following way. Okay, so it has again a theta and 1 minus theta term. Uh, this represents the first term represents the purchases, the second term represents the non-purchase. Okay. Now we'll bring in the prior term. So the first term here is what we saw. The what is new here is the prior term, which is the beta distribution. And this is how it helps in our calculation. So now we can combine the like terms. You know, theta, the like terms are combined, um, and what we end up with is an expression for another beta distribution, which has a different set of hyperparameters. Okay, so this is why choosing a conjugate prior helps us to simplify the derivation. Now the algorithm will proceed in this fashion. So we maintain counters for each product, one for impression and one for purchase. For every iteration, we sample, we sample a product from uh, the posterior distribution and find out the value of the product, which is simply the parameter value because of the Bernoulli assumption here. And we select that product and observe the reward, which is whether a purchase or not purchase. And this information is used to update the counters. And this, while we update the counter, the posterior distribution will also get changed. Okay. We'll now move on to contextual bandit. And before that, just I want to check one thing. Yeah, still there. So now the reason we need contextual bandits is we want to go one step further and want to recommend items that are personalized for each user, right? So we want to give items that a user would like. And one way to solve that problem would be to treat it as a multi-arm bandit problem for each user. So we have one bandit problem per user. Now this is not feasible because to train each bandit model means that we would need to interact with the user multiple times, which doesn't, and it's an opportunity we will not get in real life. The other reason is it is also wasteful because users may have a lot of similarity among themselves, based on their preferences, their history. And once we know about one user, we have sufficient information about users who are very similar to that user, right? So we don't really need to train independent models for them. So that brings us to context information, where this context can be user demographic, their purchase and browsing history. It can be also the other side information like what day of the week or month it is, if it is some event running, and so on. Finally, their products also can bring in some features what is the price of the product, category information, if there's some discount running. If it is, we are recommending a movie, then what's the genre of the movie, what are the actors? So they all will also carry a very useful signal for recommendation. Finally, we assume this context is made up of features. Part of it comes from user, and then the rest of it comes from the product or arm. So contextual bandit is a triplet of S, A, and R, where S is an unknown distribution of states, A is a set of actions that the agent can take, and R is a distribution of rewards, which is now conditioned additionally on the context S, right? So in a multi-arm setup, we have only R conditioned on the arm or action, but now S is the additional conditioning factor we have. So the way that this algorithm processes at each time step, the environment will present a context or a user with a context vector S. Depending on the context, the agent will select an action, and depending on the action and the context together, the environment will offer a reward. The goal here again is to maximize the cumulative reward or to minimize regret. Now, what we have seen, the MDP for multi-arm bandit has the simplest structure where we have only action and rewards. What we have introduced in contextual bandit is there are states. The action depends on the states, and the reward depends on both action and states. Okay? We're still a bit far from reinforcement learning, where we would be connecting the states together. So this is one way to model that the current action has an effect on the environment which sort of persists over multiple time steps, you know, which is not yet modeled in contextual manner. So we'll now revisit the algorithms that we encountered in Multi-Arm Bandit, and well, it turns out that all those algorithms can be adapted uh, to incorporate the context information. Uh, the good thing is Epsilon and Greedy works without any change. So just like in the multi-arm setup, we have uh, an explore step which remains unchanged. In the exploit path, we now have a model which takes in the context information and determines the arm that maximizes the objective, right? And it can be any supervised model of our choice. Okay. Coming to upper confidence bound, so we have we'll look at a particular form of the UCB called Lin UCB. So here the goal, given the context is, we want to determine which arm gives the highest reward. And in order to do that, we would need to ask the question, which arm has the highest UCB? So we'll define a value function, which is similar to what we had done earlier, but except um, that now it's conditioned on the state or context as well as the action. Okay. Now, this value function is unknown because we do not know the underlying true distribution. So we'll make an assumption that the value function is a linear model, which is why the name is lin UCB. Uh, so here, this phi is a feature transform, which depends on the context as well as the action, and theta is an unknown set of parameters or the model parameters. Now, the way the linear UCB process is that we learn theta through ordinary least squares based on the data that has been collected. So we have training data of the form, features, and rewards, and we learn theta through squared laws. Now, once the parameter theta is known, given a context and action, I can estimate the value. Okay, so we could But now it is no longer different from a supervised model. So how do we convert it into a bandit algorithms? How do we explore? Now, in order to do that, we need to define uh, we need to define the UCB of each arm. So this is the expression for UCB, which will not go into detail. You can look up the paper mentioned in the previous slide, but the intuition here is the UCB again consists of two terms. The first term is the purely due to uh, it has more to do with the observed value of an arm. Um, and the second term is about quantifying our uncertainty about that value. So if we are not very confident, our variance will be very high, and which will in effect increase the UCB. Okay. Well, now very quickly look at Thompson sampling. Now here again, we model reward as a function of the action and context, but we not necessarily limit to a linear function. So we will also assume just the Thompson sampling in the multi-arm bandit case will assume a prior distribution on the parameter. Given the triplet of observation, our goal would be to compute a posterior distribution over the parameters and then use that posterior to decide which arm we want to explore. Okay? So this is the algorithm for Thompson sampling for contextual bandit looks like. Um, the key difference, as we'll see here, is this part here where we want to compute the posterior. So for which turns out that even if we make the simplest assumption, like we have a binary reward, and the reward is modeled as a logistic regression, computing the posterior becomes doesn't have any closed form, and we need to use some approximation either through sampling techniques like Gibbs sampling or use a variational or mean-field approximation. Now, what we are going to do is to approximate this posterior and plug in the approximate posterior in place of the true posterior, and rest of the algorithm will continue. Okay. We'll now conclude our part of the talk with a summary. Um, when we look at epsilon greedy, it is easy to implement. It gives explicit control on what to explore and when to explore. But tuning the exploration budget is more of an art, and we may be over and under exploring without even realizing uh, that this is happening. UCB is computationally expensive because it requires matrix operation, um, and it may suffer from delayed feedback where the feedback is not available instantaneously. UCB, and if nothing is changing in the system, UCB will continue to take the same action. Thompson sampling is computationally efficient, but uh, uh, computing the posterior, although remains a challenge. But if we are able to draw samples from the posterior, it is much more efficient than UCB. It is more uh, empirically more resilient to delayed feedback. One intuition could be that it is not going to take a deterministic action, even if nothing else changes in the system. Of course, compared to epsilon greedy, we don't need to tune any exploration budget. With that, we'll move to the next part of the talk.
Hi, I'm Vinayak Puranik. I will be covering the second part of this presentation on reinforcement learning.
So we have been looking at bandit algorithms, multi-arm bandits and contextual bandits, where we have seen how the action taken by the agent has an impact on the immediate reward, but not on subsequent rewards. Now that's a key change we will start looking at when we now move to a full reinforcement learning setup, where we will see that the actions taken by the agent not only impact the current reward, but also start impacting the future rewards and the long-term return that the agent will obtain when interacting with the environment. And the key difference there being state transitions, and we will look into what that means and more details around that. So this part of the talk is divided into three parts. We will first start with a brief recap of some of the reinforcement learning concepts. This has been touched upon briefly by Anirban. We will look at them and their definitions once again. Mainly, we will cover three concepts. What is a policy? What are value functions, which are very important to understand algorithms? What are value functions? What are optimal value functions? So once we are clear about these three things, we will now move to the approaches to RL, and by that we mean different algorithms that will help an agent to learn how to take an optimal action when interacting with the environment. So how do we basically implement RL algorithms is what we will see in the in the second section. We will deep dive into two algorithms. We will look at a broad categorization of algorithms and deep dive into two algorithms, Q-learning and policy gradients. And finally, the third part, which is quite interesting, but we will be touching it up very briefly, which is the combination of deep learning and reinforcement learning, and how in the recent few years there have been some very interesting results, especially in the area of game playing. That's what Deep RL, briefly we will touch upon that. To start with RL concepts, again, let me flash the initial setup just as a recap, since we were now so far we have been looking at bandit algorithms. In reinforcement learning, we have an agent which is continuously interacting with the environment or the world. Now, how it interacts is by taking an action. When presented with a state or a situation, the agent takes an action. In part, as a consequence of that action, the environment presents a reward to the agent. Now, the reward can be viewed as either a gain or as a cost, depending on how we formulate the problem. And then the environment presents to the agent a next state, for which the agent will have to subsequently take another action. And this particular cycle or iteration continues until the interaction terminates at the last step. Now, as Anirban had talked about it, MDPs or Markov decision processes are good sequential, good formalisms for sequential decision making. And they, for example, in this, we have a toy MDP example over here, a full MDP that is specified over here with two states A and B and their corresponding actions. Now, this example, we will briefly look at this example. It will tell us how an agent can actually interact with with an environment and move from one state to another, right? So here there are two states A and B. Now, when in state A, the agent, if it is in state A, can take two actions. So these small dark nodes are action nodes. These bigger nodes are state nodes. So the agent can take an action one or it can take an action two. If it takes an action one, then with 100% probability of one, it will come back to the state A and receive a reward of plus 10 in the process. Whereas if it takes an action two, then there is a chance, 80% chance that it will actually, land in state B, and a 20% chance that it will come back to state A. So there is a stochastic nature of state transitions that we want to show here. And there is a reward of minus 10. Accordingly, we can also look at and reason out about the state transitions from state B. But what is important is, given this kind of an MDP, if we were to ask the question, what are optimal actions in the long term, in the long run for the agent to take? And those are the actions we have marked in red here, right? Since this is a small example, it is intuitive to see why this is so, right? Because when in state A, if the agent takes the action two, then although there is initially a negative reward, there is a very high chance that it will actually land in state B, from where it can start getting much higher rewards than if it remains in state A, right? So if we were to ask that question, we could have probably worked it out and said, this is the most optimal action from A and this is the most optimal action from B. But the question is, in real world, MDPs are much more, complex and have a lot of state transitions. How does then an agent learn how to take the optimal action is what this section is about, right? So this is just a motivation example for the same. We will also flash quickly this 4 tuple, which is a recurring theme in RL algorithms, where we say that an agent starts with a state ST, takes an action AT, receives a reward in the next time step RT plus 1, and finds itself in a new state ST plus 1. So this SARS is a 4 tuple that we keep seeing in many algorithms. In some textbooks, you will also see this as RT, where they associate the reward with the same time step, and then it's just a matter of convention. And in the literature that we followed, this was marked as RT plus 1, and the subsequent state as ST plus 1. Not to be confused about that. So moving our familiar diagram to the top, what is a policy, right? A policy is that which guides an agent to take an action given a state. A policy can be a deterministic policy, which means that given a state, the policy will tell us exactly one action that needs to be taken for the agent, or it can be a stochastic policy. So that means that given a state, there is a probability distribution of various actions that the agent can take, and the sum of those probabilities is equal to 1. The actual action is then drawn from that probability distribution. The agent's goal, the ultimate goal, is to choose actions in such a way that it can maximize the overall return that the agent gets starting from this time step, right? Which is nothing but what was introduced in the beginning of the presentation as the discounted sum of future rewards, right? So there is an RT plus 1, which is the immediate reward. Then there is RT plus 2, RT plus 3, and so on, which are discounted by the discount factor gamma squared, and so on, which can be written in a compressed format like this. But the idea for the agent is to maximize the discounted sum of future rewards. With that as the objective, the agent learns how to interact with the environment. To put this more formally, we introduce what is called as a action value function, right? Now, what is action value function? The term on the left side is what is called as the action value function, Q subscript pi of S comma A. So there is an input S, which is the current state. There is an action A. So how good is it for an agent to be in this state S and take the action A following a policy pi? That is what an action value function is defined as. Mathematically, it is defined as what is the expected discounted sum of future rewards, or what is the expected long-term reward starting from state S, taking an action A, and following a policy pi thereafter. So the first action is fixed, and then it has to follow the policy pi. And of course, the discount factor is also fixed. Now, this expression within the expectation can be expanded by looking at this figure here, right? So we have a state ST, and the agent takes an action AT, 2 of which are fixed. Now, at this point in time, the agent, this is not in agent's control, the agent can land in one of many next states. That is why first we average over the probabilities of next states P of S prime given S comma A, right? And then the quantity in this bracket, which is the immediate reward plus discount factor times what is the long-term reward from the next state S prime, averaging over all the possible actions that can be taken on the next state S prime. So it is the first state and the action, and then first averaging is over all the possible next states, and then the next averaging is over all possible actions that can be taken from the next state. That gives us the expansion for this action value function. Interchangeably, we will also call this as the Q value. And in fact, the algorithm Q learning that we will look at will help us to compute this Q value. One class of algorithms called value-based algorithms essentially set out to compute this Q value, and from there they derive the policy, and we will see how that is done. Okay. Right. So this action value function, or Q value as we call it, imposes a partial order among the different policies in a way that the policies can actually be compared. So suppose I have two policies pi and pi here and pi prime, let us say, right? So we can say that the policy pi prime is greater than or equal to policy pi if the Q value under policy pi prime is greater than or equal to the Q value under policy pi for all state action pairs, right? So that is formally how we can define that one policy is better in quotes than the other policy. So we can naturally expect that there exists one policy that is better than all the other policies, which means that the Q value under that policy is the maximum and it is better than any other policy we can think of for that MDP, right? And that is what is called as the optimal policy, and the corresponding action value function is called the optimal action value function, denoted as Q star. So there is no Q pi here, but there is a Q star, and simply this is defined as a maximum over all the policies of Q pi of S comma A. Now, why are we defining this optimal value function? Because once we imagine that we have Q star of S comma A for all state action pairs, then it is very easy for the agent to derive the optimal policy. All it has to do is run the second equation, which means that if the agent is in state S, then to decide which action to take, it has to just look at the action that gives the maximum Q value, and that becomes our new policy. That becomes the optimal policy. So if we can compute the optimal value function, then we can derive the optimal policy. I think this connection is very important because many algorithms rely on this particular connection. You can see that they first set out to compute the optimal value function. Once again, optimal value function tells us what is the maximum achievable value for an agent to be in a state S and take an action A. That is the intuition. And once that is computed, it is very easy to derive the optimal policy because I am in state S. Now I just have to take an action that gives the maximum Q value, and that becomes the policy for that particular state S. Let's just look at how to define what is an optimal value function and how to derive that optimal value function, right? The earlier equation we saw, which basically tells us what is the action value function, is also called the Bellman expectation equation, because we are taking an expectation over all possible next states, and from the next states we are taking an expectation over all possible actions in order to arrive at the current action value function. There is a small but important change we do when we try to compute the optimal action value function. What we do is we replace this part of the equation where we look at an averaging over all possible actions, but we only look at the action that gives us the maximum Q value from the subsequent state, right? So between these two equations, the only difference is this part, which is replaced now with a maximum over A prime of all the subsequent Q values for the state of S prime. So in that sense, our search for the earlier question, I think our search is on those particular actions deterministically that gives us the maximum for this particular quantity Q star of S prime comma A prime. Right, and that is what, and this particular equation is called the Bellman optimality equation. Now, these two equations are quite important because there is a class of algorithms called dynamic programming algorithms. All that they do is they convert this particular equation, the Bellman optimality equation, into an update rule. So imagine that we have implemented the Q value as a table with S on one axis, states on one axis, and action on the other axis. We have arbitrarily initialized all the Q values. We don't know about them. And then we start updating every state action pair using this equation, right? So initially we are actually utilizing equations, the values that are not fully formed. We are using initial values, but over a period of time and continuously, these values start getting updated, right? And there are proofs to show that this process ultimately converges to Q star. That means if you keep on updating it, ultimately the Q values converge to the Q star value, which is the optimal action value function. And once this optimal action value function is computed, deriving the optimal policy is a one-step look ahead that which action gives me the optimal action value, maximum action value function, and we choose that particular action. So just converting this equation into an update rule gives us one class of algorithms called DP algorithms in order to implement. But there is an important assumption over there that the MDP is completely specified, and we know all the state transition probabilities, which is often not the case, right? And that is where we move to other algorithms, which we will come to. So next we move to the second part of this presentation. We know about policies and optimal value functions and optimal value functions, approaches to RL, right? So there are broadly two classes of algorithms that help the agent to learn an optimal behavior. One is what I just briefly talked about, which is value-based RL, where the goal of the algorithm is to estimate the optimal value function, which is Q star of S comma A, which is the maximum value achievable under any policy. And once this is estimated, pi star can be derived out of Q star of S comma A. The second class of algorithms search directly for the optimal policy, which is the policy achieving the maximum future reward, or the pi star. Both of these concepts we have already introduced them. So whether we attack it by trying to estimate Q star directly, or whether we do it through pi star, gives rise to two different types of algorithms. And what does the difference mean will get answered when we look at examples for these two types of algorithms. We will first start with value-based RL. There are two broad ways in which I think this is slightly important when we look at deep RL as well, because two broad ways in which we can actually implement value-based RL. In tasks or MDPs where we have a small finite set of states, value functions can be implemented as though they are lookup tables, as I was briefly talking about the dynamic programming approach, right? So an update basically involves updating the cell value for Q of S comma A, or if you want to read a value, we are just reading that particular cell of Q of S comma A, and the Bellman optimality equation can itself be used as an update rule, as we said, to keep on iteratively updating all the cell values until they converge, right? But often in real world, we don't have small or even finite state sets. State sets need not even be discrete; they can even be continuous. So in such a situation, we cannot possibly think of implementing value functions and these algorithms in the form of a table, and that is where we need to resort to function approximation, which means that the Q of S comma A is no longer a table, but it is represented by, let us say, a neural network, which is parameterized by weight vector W. So looking up the Q of S comma A implies doing a forward pass on the neural network, saying that this is my state and action. Please return the Q value for the state action pair. And updating the Q of S comma A, and we will see how to do that, involves learning new weights or doing weight updates to the neural network so that the Q values gradually become closer and closer to the optimal action value functions. So that is how most of the algorithms, recent algorithms, resort to function approximation. Although, just for understanding's sake, as toy examples, we can look at tabular methods, but mostly everything is implemented as using function approximators. A lot of these things will become clear when we look at one particular algorithm called Q-learning algorithm, which is a very popular algorithm, goes back to 92 when it was proposed. This is this is a form of a model-free method, right? There are some salient features of this algorithm, which is what we are talking about now. Now, what model-free method says is that, what we mean by model-free is that the entire MDP is not completely specified. So we cannot assume that the state transition probabilities P of S prime given S comma A are known, right? So we will have to resort to a sampling strategy in order to know what happens when an agent is in a state S and takes an action A. There are a class of algorithms called Monte Carlo methods, which completely rely on the sampling strategy itself. In fact, the agent there does a complete episodic run, starting from the start of the episode till the end of the episode. The returns are collected and then averaged over all the different states that have been visited, and that gives rise to Monte Carlo methods. Then there are that is on one extreme. On the other extreme, there are dynamic programming methods where we know that, or we assume that, the MDP is completely given and fully specified. State transition probabilities and reward probabilities are known, and we can actually just do Bellman optimality equation updates in order to obtain the Q star value through many iterations. Q learning, and there is one more related algorithm, SARSA, that are somewhat in between, where we resort to a sampling method, but we do it one step at a time, right? So they come under a class of algorithms called temporal difference learning, or TD learning. Specifically, they are called TD of zero learning because there is a one-step execution that the algorithm does in order to know what happens when agent is in status and takes an action A. What that means it will become clear when we look at the algorithm. So the algorithm iteratively approximates the optimal action value function Q star, and these estimates are gradually updated as the agent gains more and more experience by actually interacting with the environment. Being off policy is a key feature of Q learning. Conceptually, when we look at Q learning algorithm, it looks like there are two policies. There is a target policy, which is the optimal policy that we are trying to learn, whereas there is a behavior policy or an exploration policy, which is the policy used to interact with the environment. This conceptual separation helped researchers to prove convergence for Q learning. I think that separation was a key in proving that if all pairs S, A are continuously updated in Q learning, then ultimately Q converges to Q star. There are some other stochastic approximation assumptions on the on some of the hyperparameters, but other than that, there is proof that Q learning ultimately converges to Q star because of these two policies that are sort of working in tandem. What this means, we will look at. So Q learning is one algorithm we want to look at in a bit of a detail, step by step, which is this simple algorithm we have shown here, right? So again, for the sake of this understanding, think of Q being implemented in the form of a tabular structure itself, right? There are finite number of states and actions. So Q of SA is a table. And just like we were telling now, Q of SA is arbitrarily initialized and terminal states are given a value of 0. There are two loops that occur in this algorithm. One is a repeat over many episodes, where an episode is basically agent starts interacting with the environment and terminates at the terminal state. That's one episode, right? Think of a game where an agent starts moving around in the game screen and then it ultimately reaches its destination, which is the termination. So we make the algorithm run through multiple episodes. Within each episode, we start by initializing the start state. And this 4 steps here run repeatedly for each step of the episode. So what the algorithm does is, given the state S, choose a action A from the behavior policy, which is a policy derived from Q, but there is an element of epsilon greedy in it. That means that for a small fraction of time, take a random action, whereas for 1 minus epsilon times, take an action that is greedy with respect to Q, right? Take the action which gives the maximum Q value. So choose the action. Now this is where the interaction with the environment comes. The agent actually takes the action, observes the reward R, and moves to the next state S prime. The key update then runs, right? We will deep dive into this update in the next slide. But basically, the current understanding of the Q of S, A, which is the current state and the current action, get updated using this update rule. And then S moves to S prime, and then the whole thing continues until S reaches the terminal state. When S reaches the terminal state, the entire episodic run has completed, and the algorithm now moves on to the next episode. So that way, this whole thing is running episode by episode. And in each episode, in each step, there is an update that is happening. Now, what is this about? There are two parts to this update, right? It's a weighted sum of two quantities. One is the old value, which is given a certain weight given by the step size, and 1 minus alpha times this new value or the learned value. So think of this. So this will be, again, even in deep RL, we will see the same concept that, sorry, deep Q learning, we will see the same concept that this is the target value, or rather like a ground truth that we want to learn, right? Because this is based on the actual interaction of the agent with the environment. It has seen an actual reward RT plus 1 plus, of course, discount factor times what is the maximum that can be obtained from the subsequent state. We can argue that this value is not really a well-formed value all the time, which is fine, because this is something we are learning gradually, right? But this whole thing is a target value, whereas this is the old value, and this can also be written in this following in this following way, right? Q of SA is Q of SA plus 1 minus alpha times this error term, which is nothing but 1 minus alpha now becomes the step size in this form of writing it. And the error term is this target value minus the current value. So we are making the current value closer to the target value by using this step size as our controlling mechanism, right? So the other way to reason about the update rule is, again, this is nothing but Bellman optimality equation. The R plus gamma max over A prime, Q of S prime comma A prime is nothing but Bellman optimality equation. The quantity under the expectation of Bellman optimality equation is what we want to compute. Because we don't have the MDP in front of us, because we don't have the transition probabilities, we cannot expand this expectation and do it like dynamic programming. We will have to take a sampling approach. And we take a sample of the quantity under expectation by one step of interacting with the environment, and use that as our target to learn a better Q value. That is what this Q learning update is all about. So, right. Sorry. Once we learn the Q values, and once the algorithm converges over multiple episodic runs, then the deriving the optimal policies, again, that one step look ahead that we talked about, do an argmax of Q of S comma A, choose the action that gives the maximum Q of S comma A. Because Q is optimal policy, optimal value function, what we will derive is also an optimal policy. So we are able to learn this long-term behavior without any model of the environment, being in a model-free way, even for our arbitrary MDPs. That is the strength of Q learning, right? So we will now look at policy-based RL, which is, we talked about the value-based and now policy-based. At this point, I will again briefly hand it over to Anirban to take us through this section, and then we will come back to the last part of the presentation.
So policy-based RL, as we saw in previous slides, that the goal is to learn the optimal policy, and policy-based RL takes a direct approach to find the policy, as opposed to what value-based RL does is to find the value function and then derive the policy out of it. So what we looking here is the trace of one episode. Again, we're limiting here to episodic tasks, but this can be applied to non-episodic tasks as well. So it has a start state S0, and we take an action A0, go through S1, and eventually we come to a terminal state. And while it happens, we also end up collecting rewards, R0, R1, R2. I don't know why R2 is missing. Okay, anyway. So now when we look at the return of an episode, so it is defined as the sum of all the rewards that we would collect within an episode. And the expected return is an expectation over that return. So this return is a random variable because of the state transitions that are involved, which is why we take an expectation. Then the idea is to find a policy which maximizes the expected return. Let's take a look at the terms involved here. So this expectation, we can break it down into two terms. What is the quantity and the probability of that? And to the probability, again, it can be, this term might look daunting, but it's a very simple explanation. So you start with a probability in S0, and then you take an action which is given by the policy, right? And then you have a state transition, which is given by the environment. So it's one term is what we control here, responding to the actions taken in each state. And then there is a term contributed by the environment. So product of all these terms is what is the probability of observing an episode. So the goal is to find a policy which maximizes this expectation term. Now, as you can imagine, this expectation will be very hard to compute because there are terms involving actions of the environment, which we know nothing about. So we don't have a model for the environment, and which becomes very difficult to compute the expectation term. So what policy-based methods do, and okay, before that, if we are able to compute the gradient, then we can directly update the policy through a gradient ascent. So this is the gradient component, and we take a step towards that to increase the value of the policy. The question is, how do we calculate this gradient? Because it involves computing a gradient of an expectation term, which is a bit tricky to do. So this is where the policy gradient theorem comes in. I'll not go through the derivation of the theorem, though it's not super hard to follow it. It is present in the side, and you can take a look at it offline. But the idea is that you can manipulate or play around with the terms and bring this gradient inside the expectation term. So now you see this probability. Okay, sorry if I have to go back and forth. So there is this probability term, which if you take a log, this product will translate into sum. And by virtue of this policy gradient theorem, this gradient now has been distributed over those terms. Okay, and this is also, when you consult the literature, this is known as this grad log prob. This is the gradient. This is the log, and this is the probability term. Now, how does it help is when we use a Monte Carlo approximation on top of the expectation. So we have an expectation with this quantity inside. Instead of computing the expectation, we draw a sample from it. Okay? And this will be an unbiased estimate for the gradient term. So this gives us a very simple algorithm for policy-based RL, which is known as reinforce. The key idea is you generate these episodes, you as if run the policy and generate an episode, which basically means sequence of action and reward pairs. And then you use that to update your, to calculate the gradient. So you basically make use of this term, this approximation to calculate the gradient. And then you update your policy parameters. And this follows very, similar learning steps as you do in training your model. Okay? Like in your supervised model, the way you do it. So this is a very simple reinforce algorithm. And, there are, of course, some more enhanced version of it, which combines both policy and value function directly, but we'll not go into that detail. So rather, what we have is a comparison between Q-learning and reinforce. Just to recap, so Q-learning, it uses the Bellman optimality condition to learn the Q function, and the policy is derived implicitly from the value function, optimal value function. Whereas reinforce learns the policy directly using an MC approximation. Now, if your action space is large and potentially continuous action, then it will become difficult for Q-learning because you have to compute it, compute the an argmax state on the value function to come to the optimal action. Whereas in reinforce or in policy-based methods, since you are learning the policy directly, even if your action space is continuous, you can still calculate the gradient with respect to the action as well. Another big difference is off-policy learning. So this is sort of like a boon for Q learning, because you can make use of a lot of historical data that has been collected, as we were discussing in Vinayak's session, that we can also train a learning agent from historical data that has been logged from another agent, which is known as off-policy learning or training. Whereas for reinforce, it needs to interact with the environment always. So that means it cannot make use of the data that has been collected by other policies to train to learn the policy function. Q learning has a high bias because of the approximation step that is involved, where we are sort of training the where we are sort of learning the value function with respect to a noisy target, and we are continuously refining the target, so it leads to a high bias in the estimates. Reinforce, on the other hand, has a high variance due to the sampling step, because the sampling might introduce variance, and it also, in an effect, it also contributes to the slow convergence of reinforce as compared to, say, a Q learning.
So in this concluding part of this tutorial, we will be looking at deep reinforcement learning, which is a combination of deep learning and reinforcement learning. This is going to be more at a motivational level. We want to give some high-level examples, and we may not go into a lot of details here, right? Most of the material in this section we have taken from the papers from DeepMind, where they talk about how they train an agent in various game playing kind of setups. So that's what we start by motivating. In the last few years, maybe like starting from 2013, we are noticing a lot of papers coming from DeepMind on how they train a deep RL agent to play more and more complex games. So in 2013, they published this paper, Playing Atari with Deep Reinforcement Learning, where Atari 2600 is a video game console. Rather, now it is an RL test bed, which is out there for RL researchers to test their game playing algorithms, agents. And it provides a suite of arcade games for the agent to compete and play, right? So they published this paper where a single model architecture, with a single model architecture, they were able to train the agent to play 7 different games, all by just observing the screen pixel from the screen of that console, right? So there is no additional game-specific domain information encoded into the agent, or the logic of the game is not encoded into the agent. The agent just looks at the screen pixel and based on what it sees on the screen, interacts with the environment and earns a reward. Just by this, they were able to achieve expert performance on multiple games. They followed this up in 2015, where their article appeared on the prestigious Nature magazine, where they were able to extend this architecture to play 49 different games, many of them at expert human level performance. Then came in 2015 or 16, I'm not sure, AlphaGo, where they were able to train an agent to play a more complex, rather than just arcade games, to play a more complex game called Go, which is a very highly intuitive game. There are a very large number of board configurations, and the agent will have to learn to take some very long-term decisions in order to have a winning strategy. And then they came up with this paper called AlphaZero, where they were able to combine not just Go, but multiple such strategy games, chess, and there is another Japanese chess and so on, into one single architecture. More recently, they have come up with AlphaStar, which is the first AI program to reach a top level performance in StarCraft 2, which is a real-time strategy kind of video game, where there are multiple levels and multiple races. It's a multi-agent play here, where there are multiple agents that are sort of strategizing to win in a particular contest, right? So a lot of these recent advancements have happened by combining deep learning and reinforcement learning. We will now go back to Atari as it is a simple example to understand. This is the same setup that we saw in the beginning of RL on how an agent interacts with an environment. Only here the agent has been replaced by this entity, which let's assume is again an RL agent, a deep RL agent, which is trying to learn how to behave optimally in this game playing setup. It is interacting continuously with this environment, which is the Atari console. What it gets as a state information are these screen pixels continuously, which tells what is the current configuration of the game. It takes an action which is primarily moving the joystick. Either it could involve moving a paddle to the left or the right, or shooting a gun or something like that, which then has a feedback on the game itself. The reward is nothing but the points that are collected on the top of the screen, and the agent learns to look at the reward and say that as the rewards increase, that means the agent is performing better and better, right? So just with this sort of a setup, they were able to design a game playing agent. Now, the question briefly, why do we need deep learning here, right? The authors of this Atari 2600 paper, they did a lot of optimizations on their state space. They first of all took the last 4 screen images, the screen images of this type, right? They took the last 4 screen images, probably to get a sense of direction of the paddle or direction in which the game is going, resized them to 84 by 84 square area, and converted the color coded pixels into gray levels, to 256 gray levels. In spite of all these compressions, the number of possible game states is very, very high, which means that it cannot be possibly just encoded as a tabular approach, and hence we need a function approximator that we talked about. This is where the deep neural network is coming into picture, because the deep neural network helps us to approximate the q value, q of s comma a, parameterized by the weight vector w, and help us to learn better and better q values. In a nutshell, how are we sort of combining deep learning and reinforcement learning, right? Deep learning is giving us this power of representation learning. We don't need explicit domain knowledge to feature engineer, but we can start with these high complexity sensory inputs or raw inputs and learn robust representations, as we have seen in a lot of deep learning papers in the recent times. Given an objective, DL can help us to learn these representations. Reinforcement learning gives us the power to act optimally, to take decisions such that long-term rewards are obtained in an optimal manner, right? So what we are essentially doing is combining these two, the deep part, which can help us to process the raw complex input and learn strong embeddings or representations. Reinforcement learning is helping us to choose complex actions given this representation, and thereby helping us to achieve the goal of AI, which is almost, in these kind of game playing setups, giving us a human-like performance when playing these games. We will briefly look at Q learning, revisit Q learning. As we saw, Q learning is nothing but implementation of this Bellman optimality equation. How we saw in the earlier Q learning algorithm how the quantity in this expectation is sampled through experience. That is exactly done even in deep Q learning as well. We treat this right hand side, the quantity under the expectation, as a target, and the current value of QSAW as the source or the current information, and loss is nothing but the error between the target and the current value. So we basically compute the mean squared error loss and run a stochastic gradient descent to minimize this loss. And that is how we combine Q learning with a deep neural network, right? Now note that in this particular case, even the target actually depends on W, which means one can ask that will the target not keep changing as the network keeps learning, right? So there are some optimizations that the authors have proposed, which I will come to. But yes, there is a target which also depends upon the Q network, and then the current values of Q that are updated according to this target. This learning is very similar to the standard supervised learning that we do, except that how the target is formed. In a supervised learning setup, this target is already given to us in the form of the Y value, but here this value has to be formed by actually interacting with the environment. So there are two ways in which you can set up the Q network, right? One is, as you just said, that the input to the deep neural network is the state and the action, and the output is the Q value for that state action parameterized by W, which means that if there are a large number of actions, we will have to do multiple forward passes with each action in order to obtain the Q value and then take the action that gives the maximum Q value. The other way that the authors have chosen to do here is take only the state features or representations as input and have an output for every action that has been decided upfront for this particular game playing. So for example, in the Atari console example, they have 18 different actions. Probably every game may not have all these 18 actions, and many of them could be even no ops, but that is probably the maximum number of actions that they need to be ready with, right? And they take the state, and in one forward pass, they get the Q value for each of these actions, and then they can choose a max over this. While the action space can be very large, the state space itself is definitely very, very large, as we saw, right? And that is where the deep neural network is coming into picture, that possibly not all states may even be visited by the agent when it is playing or when it is actually training, right? So it is the generalization power that this network is bringing from seen states to unseen states, possibly in the way they share the features or through some complex representation. There is some feature sharing that is happening, right? So that's where the power of deep learning is helping. So what the agent is actually doing here is building these SARS kind of experiences. So these are again some optimizations that the deep Q learning authors have taken in order to make work around this problem of RL data not being IID, to be able to use a deep learning solution, right? So what they do is that imagine an agent is continuously interacting with the environment. So they collect these experiences of state, action, reward, and next state into what is called as an experience buffer with a fixed size, right? Now they don't do an update on every possible step. This particular weight update is not done on every possible step, because that will introduce the problem of correlations, right? Each data is kind of correlated with the previous experience. Each experience is correlated with the previous experience. Instead, what they do is, once they have this buffer of data, they sample the data to remove these correlations, randomly sample some number of data points, and then they run this weight update. So once they sample this data point, you can see that all they need is SA, S prime, and A prime. A prime is coming from the network itself because they want to take the maximum A prime, correct? So once they get SA, R, and S prime, that's what they need in order to make this, in order to apply this weight update to the network. So, but another important thing to note is that, again, if the targets are continuously, changing, suppose they were to use the same weight vectors, then they were facing a problem. Again, these are a lot of tricks. When you read the paper, it feels like, as though they have tried a bunch of these things and looked at what works the best, right? So probably they observed that the weights were diverging because the target is also continuously changing. So what they do is they have a parallel network, right? So they keep the targets fixed for a while, for some number of iterations. And when they are doing these weight updates, the target part of it is fixed for some time, for some number of batches. And then after some time, they switch the network. So the old learned network now becomes the target network, and they continue to learn. So some of these tricks is what they need to apply in order to make deep learning work in the context of Q learning, like building this experience buffer, this buffer of experiences, sampling from it, and thereby breaking the correlations, and then sampling experiences in order to do the weight update by keeping one of the parameters in the target fixed for some time and only doing the weight updates every doing the weight updates for every few set of batches and then switching the target network, right? So uh, all these things are sort of encoded into this deep Q learning algorithm. Unlike the deep learning algorithm, we will not be going into individual steps over here. But the reason why we are showing it here is just to show that this is nothing but deep learning. What we saw in nothing but Q learning, I'm sorry, because what we see is a set of episodic runs from 1 to n. There are a set of episodes. The initial state is initialized, and then for that episode in steps 1 to t, the entire Q learning algorithm is actually running. The only difference between this and the original Q learning that we saw is how experience replay gets added, right? Once the agent takes an action and this experience is formed, this experience is not used to directly do a weight update, but actually to store it in an experience buffer and then take a random mini batch of these transitions and to run the weight update and periodically updating of the target network, right? So that convergence can be achieved. So just wanted to show this high level picture to show that what they're doing is exactly Q learning with these additional steps in order to make it work. So their overall network architecture looks something like this. They have a stack of 4 previous frames that together forms a state representation, then a bunch of convolutional neural network layers, followed by a fully connected output layer with 18 possible actions for 18 joystick or button positions. So they take the state as an input and give an output for each possible action, right? And with that, again, this may not be very clear, but these are on the x-axis. We have these different games, and on the left side of this line, there are these bunch of games on which they were able to achieve or even beat human level performance, right? So this agent learned to even play better than a expert human level performance, and on some other set of games which required a longer time frame of a longer window of interactions, they possibly did worse than some other set of games. In fact, how they do it, I just wanted to show a video just to demonstrate one of their game playing agents. Just a second, let me just open that. So this is where the algorithm will play Atari Breakout, and they show how the agent is initially very clumsy in moving the paddle and how slowly it kind of learns what is the right strategy to move the paddle to be able to break the bricks or whatever. Just read through the screen. So initially it is making a lot of mistakes as they are showing. After considerable amount of training, it is able to move the paddle very accurately. So just by sampling the screen and with a lot of training, by playing a lot of these instances of these games, it is able to recognize these strategies, right? So this sort of concludes a brief section we had on DeepRL. We just wanted to quickly motivate how we are getting some great results in game playing with DeepRL. So in conclusion, we talked about multi-armed bandits in the first part of the presentation, where we looked at 3 algorithms: epsilon, greedy, UCB, and Thompson sampling, both in the context of plain multi-armed bandits and contextual bandits. We then moved to reinforcement learning. Specifically, we looked at 2 algorithms, Q learning and reinforce, which is the policy gradient And then we also looked at the deep Q learning as briefly as a motivation on combining deep learning and reinforcement learning.
Finally, we wanted to share a set of resources that we have referred to for this presentation, which you may also find useful. Thank you.